let's push on with the final session. We have 3 presentations, each of which is a case study, so we can see how a lot of this comes together into making a real project happen. First speaker this afternoon is Bryn Phillips from Wardenburg, contractor, and his case study is Castle Rig, which I think we've seen a quick sneak preview of just a few minutes ago. Bryn.
So I'm Bryn Phillips from Wardenburg. I'm just going to talk through Castle Rig, which you mentioned a couple of Christmas up in the lakes. So just a brief introduction of what I'm going to cover. Just a brief introduction to Wardenburg, so who we are, kind of what we do for those who didn't ask. I've slotted in a couple of extra slides there just about the shafts, that you can see here, because that was mentioned earlier. I thought may as well pop them in since I've got them. And then just the drive itself, a couple of bits about the equipment we used, and why I kind of selected it. Then sort of 3 lessons learned, and a little bit on the research that we're doing at the moment as well. So this last slide down here. So firstly, a bit about Wardenburg. So we operate in the Republic of Ireland, the UK, Canada, and North America. These are kind of a vague map of some of our active sites. I will add that not all of those are tunnelling. So what we are is a design, build, operate contractor for wastewater treatment works and potable water treatment. But a lot of the work we do, especially over in Canada and the States, is pretty much flat out micro-tunneling the entire time. We own 25, we think, Heron Connect AVM machines, which is no, we won't let Heron Connect inventory us apparently and see how many we actually have. So it's a surprise. Founded in 2001, and generally we do in the drive range 600mm to 3 meters ID. So that 3 meter ID has been done over in Canada, and it's quite a sight to behold, to be honest, the size of the pipes. So very briefly, these slides are just added in on shaft construction. So we talked about obviously all different kinds of shafts today. Our preference and what we'll normally use is an in situ caisson, which is a top-down method of construction. So essentially you have this as a reinforced concrete wall that you can excavate either from the bottom if it's dry, or if it's a smaller diameter and it's wet, you can excavate it from the top. What we have done as well is excavated the rock using a breaker on like a 50-ton machine with like a 3 meter extension arm, and we got down to depths of about 18 meters, 18 to 20 meters without digging from the top. Again, what we talked about, so flooded condition, pouring a base, unreinforced plain concrete base using a tremie. This was next to a railway up in Morecambe, and this is from the same job, and this was the material we were tunneling through. Some quite large boulders we were found just at the level we were tunneling, which is always slightly less than ideal, but that was fine for a finish. Yeah, exactly. And then this is just a little video. We talked about the helical shutter system, which isn't something we use for the smaller shafts. What we use for the smaller shafts is essentially like a jump form to do the in situ concrete pours. But for the larger pours, we developed this system with constructs, which is essentially a helical system that goes along and you sink and pour at the same time, and we go around. So this was the first of the tanks that was 30 meters internal diameter and 30 meters deep. It was 8 million liters, 12 million liters, I think, of storage. There's a second shaft on this side that was 32 meters internal diameter and 17 meters deep that we use the same system for. These were both in Blackpool and Anchorshome by the beach. So the driver we had for this was one to create a jump form for this. It's very expensive, it's a lot of shuttering panels, and it's a lot of concrete to have to do per lift. And you have a cycle time of over a week, say, for that one lift. Whereas with this, we were pouring 55 cube a day, 8 pours round to complete a ring, and 88 pours in total. And by the time we were up and running, after like a little bit of teething problems at the start, we were pouring one of those per day. The final thing to add on that, it has this leaning platform here, which you use for putting the rails to pull it and fixing rebar, etc. And then there's this little trailing platform here, which is used for rubbing up, filling tie holes, all that kind of stuff. So that removed any need for working at height, or from, well, not necessarily working at height, but for working from man baskets, which again is another consideration with the fact we were next to the beach and it was very windy. Just very briefly as well, underpin construction, you've seen some slides for segments. We again like our in situ concrete, so this is a shuttle we've adapted to do in situ underpin. What essentially it is, it's a kind of a conical shaped shuttle, so it's 7.6 say at the top and 8 meters at the bottom. We have a few sizes of them. What you essentially do is jump down in these 2.5 meter lifts all the way down to the bottom, and then you do 2 kind of straight vertical pours at the bottom to use as your thrust wall. and they're directly poured out against the rock with a shear key in to help withstand the sort of the weight of the actual shaft as you're underpinning it, and then that also helps in the long term as well if it's a permanent shaft, so you can plug the base and those shear keys then resist the uplift as well. So onto the Castle Rig Drive. So it's part of the United Utilities West Cumbria Water Supplies Programme. So what this is Ennerdale Water down here. You use abstraction licence 4 runs out in 2022. So they have to find a new way to get water basically to the west coast, up near Whitehaven and Sellafield and those kind of areas. So what they've decided to do is pick the Thermo reservoir over here and bring the water all the way across to a new water treatment works at Williamsgate near Cockermouth, and then pipe it all the way around. So this handy bit on this map here is the Castle Rig Drive, this pink section, and you can see what the drive does is it avoids this very long diversion round a hill essentially, having to go over the river twice and under the main road, the A66 as well. So within that scheme, in the Keswick area, there are 4 tunnel drives, which we had, which are all complete, and there's one further drive at Cockermouth over here, which we're starting on Thursday. So the drive itself, 1,241 metres long, so fairly long. It's about 100 metres of till shown on the GI kind of at the start here, 1,000 metres then of mudstone, and then about 150 metres more of till with some boulders in as you come out the other side. So the key thing I guess here is that we're in this mudstone the whole way through. It was very, very low, fairly low strength, so weak to very weak, and very low abrasivity, which is kind of the ideal really for tunnelling through, because it meant that we weren't expecting a huge amount of wear on the cutting discs or anything for the duration of the drive. A couple of points just to say about SI, and we've kind of gone on a lot about it today, so I won't labour this too much. At the start, this long section, there were no boreholes immediately where the shaft was, so what we actually found was, like you can see here, it was going straight into the mudstone, but we ended up with 100 metres of till before we entered the mudstone. In the middle here, one of the boreholes showed conglomerate during the tunnel drive, which is a sort of a cemented sort of sands and gravels and things that form in the outflow from the glaciers and things and all the mudstone formed. We didn't actually find that during the drive, but it was something that flagged us that there may be some more aggressive material for wear on the cutter heads there. And the final thing was about 600 metres in, we actually encountered quite a large, well not necessarily large, but an open fissure. So what we found is instead of this very low permeability mudstone where we were having no water pressure building up on the head, when we went through here, the pressure suddenly jumped up to sort of 2.5 bar. So it's just, again, another consideration for SI, not always sort of showing everything. So what has to go through the drive for a finish, I guess is kind of the important thing. So there are twin 40 metre long, 800 diameter steel pipes going in. So we've just completed pulling these through the drive now, and we pulled them from one end to the other on spiders that we put in. In addition to that, there were 210 mil PE ducts that were put in kind of on the side of the tunnel wall as well. It's going to be sealed and filled with water on completion, so we had to deal with corrosion and making sure that there's anodes in there to protect the spiders and the pipes themselves from corrosion in the water, and it has a 60-year design life. So in terms of the equipment that we used, just going to go through this. So the machine we used was actually I'll come on to that one next. The pipes themselves are 2026, 2756 diameter wet cast concrete pipe, which we get made over in Tracy Concrete in Erskine and in Northern Ireland. The reason we go for wet cast generally is a very high quality and finish, and also you have this feature here, which is a very helpful thing that we quite like, that is essentially a little rebate that holds the primary seal in place. It means that especially on these long drives, if there's a high external pressure on the seal, as the pipe joints sort of slowly articulate, what we found in the past is that these primary seals can try and work their way backwards, and can come off and cause leaking into the tunnel. So this little kind of step there holds them in place, which again is something that we think is a fairly key feature. I guess we've talked about jacking forces and axial capacity as well today, and we're just saying that had a 1,700 tonne what we say working jacking force, which isn't the perfect condition. That's the condition where it goes from a zero load at one side to the maximum force on the other in that kind of linear stress block distribution. So in terms of the TBM, AVN 2200 from Heron Connect, named Diggory by the people in UU. Still not overly sold on naming TBMs myself. We did this with a mixed ground head so that we could cope with the till and those kind of things that we were expecting at either end of the drive, and knowing that the mudstone in the middle was weak to very weak, so we didn't need a full rock head to do that, because as we break it up and go through it, it's going to form into these small chips and also ultimately start to break down into being clay again. A key feature, as the main reason for this one, is we had a a 10 kilovolt high voltage power feed to the TBM. Now I think HK will call it medium voltage, but anything more than that would be a little bit scary, I think, for myself. But so we call it high voltage. The main reason for this basically is by stepping the power all the way up to that voltage, you have a smaller current flowing through the cables up to the TBM. And what that means is you have reduced power losses over the 1.2 kilometre length of that cable. That enabled us to have a single power cable that went up to the head of the TBM, which powered the TBM itself, the first 2 tunnel pumps, and all of the kind of ancillary items up there. So the VMT system, lights, kind of other little turret pumps that we have in the tunnel and those kind of things. So this is a little schematic of what then came along with that. So we have the TBM obviously up here, and we have space here for our first tunnel pumps. So we actually had 2 pumps put in there, a service pump and a spare. We'll talk about that a bit later. And then after that, what you have is these 4 gantries rather, that contain all of the transformers to step that 10 kilovolts back down and sort of control all of that process. And then again, behind that, you'll see a bit later, we have a load of other spares and things stored there for if we need them. I guess the pros and cons of this system, obviously it's expensive to buy, and also, sorry, it's very reasonable to buy.
I'd like to say competitive against the alternative.
Definitely competitive, and for a finish it was a lot less faff than having to run 3 cables up to the head of the TBM to do the power up there. And also obviously, so there's this extra space that's taken up by it, but again the advantage is this single cable and the kind of benefits that are associated with that. I've talked a bit about the shafts, just to say that they had a 1400 ton jacking frame in the launch shaft as well there. So the jacking frame was slightly under-spec for the pipe, which was okay. And it's kind of a toss-up we have in the company about whether to over-spec or under-spec the frame normally. Because if you under-spec it, there's no way you can put too much load through the pipe and break the pipe, but it means you can't ultimately mobilise all of the capacity that the pipe has. So there's kind of pros and cons to that as well. We've talked quite a lot about instruct stations today. This is just an example of one of the leading pipes. So you can see the blue steel can there, the instruct rams inside, and this is just a temporary push block for installing it that goes in the back and then gets lifted out before the next pipe goes in. So the idea behind these, as we've said, we had 9 of them in to reduce the risk of getting stuck essentially during the drive, because at 60 metres of cover, passing quite near to a scheduled ancient monument and in sort of on the edge of the national park, digging a rescue shaft for anything wasn't really going to be an option. So we thought we'd try and avoid that. So we reduced the risk, but obviously there are costs associated with that. The first one being each one of these is a fairly specialist item and costs a lot to fabricate. It also takes additional time to install, so there's programming costs associated on the site with that as well. And then also obviously you have to strip them out at the end, close them up, so there's additional costs and programming involved with those as well. In terms of lubrication, again, HK automated system. What we actually had, because of the length of the drive, was we had 3 separate bentonite feed lines going up the tunnel. So the first bentonite feed line fed the TBM and the first 8 boxes, I think, after it. The second one then fed sort of the next 40 boxes coming back along the tunnel, and then the third line fed the remaining. So what that meant is that if you had it all on one line, say, if a box opened here, it's likely that the pressure at the front wouldn't get back up to high enough before when you open the valve, so you wouldn't actually get any bentonite injection there. And that's something that we actually found when we configured the system wrong, so that one of the boxes back here in the launch shaft was opening accidentally twice. We found that we were actually under-lubricating further up the drive until we managed to work out what was wrong with that and set it up and got it sorted. Again, they were fed by 2 separate Gertech units, which are the kind of mixing and pumping plants for this. I guess 2 reasons for that. 1, the amount of bentonite we were pumping required 2 to pump it, and 2, you have a redundancy. So you essentially, in a worst case scenario, one of them breaks down or has to stop for maintenance, you do still have one that you can run. The output of that pumped 6 million litres of bentonite lubricant into the hill, so it's fairly well lubricated in there now, but that meant we had an average skin friction of 0.6 kPa when we finished the drive, which is fairly low. And that one especially meant that we only actually required the instruct stations right at the end of the drive. We had to use the first one because we went into more mixed ground to break boulders and things, and they were only really required though after we had stoppages for any reason. So I guess I'll move on now to a couple of lessons learned from the work we did there. The first one I always like is trust the surveyors. So 1.24 kilometre drive, as we said, driving uphill at a 0.04% grade, so not a very steep uphill grade. We used a VMT automated total station guidance system, which required resurveying and checking every about 100 to 150 metres. Towards the end of the drive, the resurvey process and the check process was taking in excess of 3 hours. So there's a lot of downtime there, a lot of stoppages to check this, but it's worth it because at completion we were 19 millimetres left of alignment and 29 millimetres low, which is fairly impressive if I do say so myself. The second one is about repair and replacement of stuff. So this is looking from just behind the gantries up towards them. So these red bits here are the transformers for stepping down. This is the main power cable that you see, which has the 10 kilovolts in. This yellow one coming back is going back down the tunnel to power one of the pumps. And then you have your feed and return lines and the bentonite lubrication line going up there towards the front. So kind of in terms of gear that we put into the front of the tunnel, knowing that we didn't want to have to carry it up 1.2 kilometres if something broke towards the finish. Spare grease, you can see up here on the shelf, a full set of spare cutting discs. In front of this there's a tunnel pump, and as I said, a whole spare tunnel pump as well. And sort of various little small tools and things, because it's not really somewhere where we want to go and then realise you've forgotten your spanner or something. By the end of it, and I guess these are the kind of lessons learned out of this, all of the spare pump, all of the bits you could take off of it had been stripped off of it and put onto the service pump to keep that running. So that if that service pump then had a catastrophic failure for whatever reason, we would have had to come back up the tunnel with other, albeit small replacement parts, not an entire pump, but replacement parts. So what we're looking to do in the next one of these long drives that we do is, as well as having a whole spare pump up there, we'll have a complete set of all of the pieces that will likely wear out, and we're now very much more aware of what is likely to wear out as well. This was quite an interesting one. So the grease that we were using, so for lubricating the pumps and everything else, a lot of that ended up dirty, and you ended up with small particles of grit and things in the filters that were feeding the pumps, which meant at points those filters blocked, so the pumps weren't getting lubricated properly, which meant increased wear on them. And what we kind of realised what was happening was all the way up there, the guys were going up there and they'd have their gloves on from doing whatever else. The gloves would be a bit dirty, and they'd just go in and you take a big handful of the grease out to top up the feeder for the pump, and all the crap off your hands goes obviously in the grease and into the feeder and can block it. So what we've said is in the next one we'll just take up there a couple of boxes of latex gloves, so the lads can take off their gloves, put on the latex glove, and then it's nice and clean when they actually do the greasing. And it's kind of those kind of really simple small things that actually very nearly cause us big problems.
One thing I will note, at least your lads were greasing the gear.
Yeah.
Fail or no fail.
Yeah. But it's something that one of the drivers pointed out, that a couple of points they would go up and check, and the grease pot in the pump would still be full, and they'd be like, oh, it's full, it's fine, I don't have to top it up. Maybe not quite thinking it's full, it shouldn't be full, something is wrong here. But again, it's just a little lesson learned. So when we received the TBM into the launch shaft, we were amazed, to be honest, at how little wear there was on the head, like all of the hard facing and things were still intact. But one thing we did notice is that after going a kilometre, 10 of the bearings within the discs themselves had failed, which meant that if we had to go much further, we would have started to have issues with uneven wear on the discs and mushrooming, so they would then need to have been replaced. Which again is something that we had prepared for, so we had spare discs and spare bearings up at the front of the drive, but it's just something that we just another interesting point to see, I guess, that it was the bearings that went as opposed to the actual discs themselves wearing out. The third one is about water pressure. I'm probably going to get kicked to having this slide in. So this is one of our instracts, and that's not how instracts are supposed to look. So what basically we had is, it's quite lucky we had an instrumented pipe as part of the research I'll talk about at the end, located 9 metres behind one of the instracts that we had in. That recorded a maximum pressure of 5.5 bar in the annulus of the pipe. So the hydrostatic pressure that we were experiencing during any of the stoppages in the mudstone was only 2.5 bar. So during our lubrication regime was over-pressurising the annulus by essentially 100%. And this 5.5 bar is quite close to what the seals are rated for, at 6 bar external, and also what the IJS cams can cope with. So what actually happened during the drive was one of the IJS cams, like I say, IJS cam 5 buckled. I'll talk about that a bit more later. As it buckled, it opened, this gap here has to be very tight to keep the seal in. That gap opened slightly because of the buckling, which meant that the seal could then be pushed by the water pressure through. and we then had as you can see there, a leak of the bentonite coming back in through the seal into the tunnel. So what we then had to do to fix this was we went out through the interjack pipe and drilled out through and injected it with resin. And we basically essentially resined that interjack shut, but what it meant was it stopped the leak, but we then couldn't use that interjack again during the drive, because if we did, it would have just broken the resin and opened up the leak again. So I guess there's a couple of considerations here that we need to think about. Is our interjack design itself sufficient? Like, do we need a thicker can on it in order to resist these kind of higher pressures in the annulus, or whatever caused it to buckle? Or is there some way that we can use, for example, the cradle that holds the interjack rams in place to actually support that can and stop it buckling? And this one is the support the can is probably what we're leaning towards more at the moment, because it avoids having to retool all of the pipe molds and things. Finally, the next question, which is again as part of the research we're looking at the moment, is that 2.5 bar of pressure in the annulus for lubrication, is that actually required? Is that beneficial? Or are we just pumping in bentonite like crazy because it's a lubricant, but actually it's causing us problems like this, and potentially it's actually increasing the skin friction, because in a way we're forcing more and more solid material into the annulus that may not need to be there, considering that we're in rock and this is a stable bore. We think it was a stable bore anyway. So those, I guess, are the kind of three big pointers that I think I take away from this that I kind of wanted to share there today. And now I'm just going to talk very briefly about the research that we're doing. So Wardenberg as a whole, we've engaged with a number of universities in UK, Ireland and Canada doing sort of various bits of research and putting people through masters and PhD programs. I'm going to talk about Oxford because that's where I'm involved with. So we're part of this focus group, it's called, which stands for Fibre Optic Monitoring of the Construction of Underground Services, or Structures actually I think, which is led by Dr. Brian Shield and is sponsored by the Royal Academy of Engineering as well. So what we're trying to do with this is basically optimise sort of various aspects of underground construction work and try and improve the design methods for them potentially, and also just to use fibre optic sensors to get more information about the forces that are on these various items whilst they're under construction, and then also during service as well. So the first part of the research that we did was on our case on silo construction that I talked about earlier, and we basically look at a number of parameters, so annulus performance, the forces and strains within the pipe wall itself, and we also developed a levelling system that we now use for the shafts, which is similar to the water levelling system that's used in the TBMs as well. So then this is now sort of my area of research, which is on the tunnelling. So we're kind of looking at lubrication mix design and performance of that over time, live monitoring of pipe performance during installation, and then also jack and post automation, and then on that having got bearers, potentially looking in the future to do longer term kind of service monitoring of pipe strings that we've installed. So what we did for Castle Ring was we developed this instrumented pipe that basically had a number of strain gauges cast in around the perimeter. And what these were measuring is the axial strain within the pipe, the hoop strains within the pipe, and also a kind of 45-degree plane shear, so that we can define how the stress state is within the pipe wall. We also had load cells in the outside of the pipe, which at the four corners. I won't talk about those because they broke. And pressure transducers as well that were directly measuring the pressure in the annulus of the pipes I mentioned before. So that's what this plot is here. Shows the pressure, so you can see up here before we had the leak, we topped out about 5.5 bar. And then you can see down here where we were down under 1 bar, that was where we had the leak in the interjack in front of the pipe section. So it's quite an interesting kind of plot of the development of the stresses there. You can see how much it changes just even during the normal process. Coincidentally as well, this peak appears at about the layer position of that fissure that I talked about in the SI earlier as well. Yes. Oh shit. So very quickly then, just on that point where the can buckled, this is the bending moments that came out of those strain sensors. So if I play that, so what you see is this is as the pipe's advancing, you see it's fairly stable and there's a little bit of an inward moment at the top, and then as we go past about 590 metres or so, you see it gets a bit less stable, and then that happens there with the red dot where it goes all the way in, and that is what we think potentially actually caused the can to buckle. So the can was under fairly serious stress by the pressure outside, and then some sort of a little bulge or something in the top of the annulus. Yeah, exactly. Just a little bit of something to clamp the matrix, and just pushed it in, and that was all it kind of took. Similar to that as this one, we've talked a bit about the forces today that run through the pipes. What this is from the axial sensors is the centre of effort, if you like, of where we think the force was through the pipe. So if you imagine if it was bang on the centre, it would mean the forces are evenly distributed around the perimeter. You see it's not too bad, it stays fairly well within, but again when you get over to this point where the can buckled, when we went past that point, you kind of see it there, it kind of shoots out to the side of it. So there was something funky happening in the airness at that point anyway. So I think that's me.
Thank you.
I promised to put us back on schedule, so yeah.
Thank you. I deliberately let you go on over the time because it's interesting and we're here to hear what you say rather than to keep to a timetable. But Richard is up next. Another case study, Army Bay. Richard. You've got 2 minutes now.
I've got 2 minutes, as they say. Client, consultant, and the designer are all out there full-time, plus the contractor's still got to do it on time. Okay. Right. There is a caveat with what I'm about to tell you. It goes a little bit along the same way as what Bryn's just said. Right machine, right ground conditions, enlightened people on the bid. Okay, we make a product direct pipe. It's predominantly made to challenge the HDD market in shore approaches, which is where it came from first of all, or river crossings. It's designed to mirror HDD, and same distances but larger diameters, so 4 foot, 5 foot. It can do. So Army Bay was in New Zealand. It's the longest ever direct pipe, 1,930 metres. It had both vertical and horizontal curves, and it was the deepest direct pipe. Deepness comes out of all the mechanical engineering that goes into the machinery. Bryn talked earlier about 5.5 bar. Most tunnel machines are made for about 5 bar. You can ask for them to be made bigger, but it starts having an effect on the bearings, the bearing protection systems, sealing systems, and a lot of other things. Pressure is quite a killer. Okay, how was it achieved? Basically, everybody who was involved in the scheme got involved at a very early stage and understand their roles. Okay, so the alignment of the planning was done with our help. The contractor obviously had chosen Aeroconnect. The contractor was McConnell Dow, by the way. Our people joined with them at the tender process, although they had partly won the scheme on a microtunnel, or part microtunnel, part tunnel. The location is ground conditions mainly, but so be it. That's the alignment. Yeah. Jim's looking at it, scratching his head, saying, "Pipe jack." They started here at the wastewater treatment works and ended up out here in the sea. Two intermediate shafts that they were able to put in, they were not very big, but they put them in specifically because the machine wasn't that large. It was only an AVM 1200, yeah? It's not that big a machine. You can make it with hyperbaric and face access, but you need leprechauns in some way, shape or form to do it. It's not an easy job getting in there, and it's not something you'd recommend. But you can see there's 2 horizontal curves, there's a vertical curve in all of that as well. They were the intermediate shafts and maintenance shafts. So as Bryn said, although the ground was ideal. Although they went and looked at the machine as it came through these shafts, the head was actually very, very good, and the teeth were 98%, so they didn't even bother changing them. All right, so it says they changed some, they changed 1 or 2, but they were ones that had been smashed rather than worn away. And they had 1 or 2 other issues that they could do and did do while they were going through. That's the setup. It's a monstrous great setup. This is the machine. As you can see, it's about 15 metres long. Pumps, guidance, and such like. These That's a 750 ton thruster, and that's a 500 ton thruster. So they had 1,200 tons of thrust, all from the back. There are no interjacks. It's a steel pipe, so that's the steel pipe strung out, just like you would see on an HDD. They were put in, I think they were 125, 150 metre lengths, and they obviously were lifted in and welded on. Big set of rollers out the back. Some idea of the kind of amount of equipment 30 shipping containers full. That's just our equipment. That includes the pipes. That's just hoses, pumps, cables, guidance system, water levelling, you name it. Risk sharing. Not that this really tells you the truth of it. The client knew that the compliance scheme was going to cost him in excess of £50 million in the UK. And he knew this was going to save him a large amount of money. So the client took the risk. The client was involved in all the risk planning with the contractor, design of the GBR. The contractor took some of the risk, but not all of it by a long stretch. Okay? And even Aaron Connect had to take some of the risk to do with the various performance of the machine. So we were in a version of, not quite back to back with McConnell Dow, but certainly our reputation was on the line, and so we, whether we were back to back or not, we still had to perform as if we were. These are the people we put on the job, and I only put it up to highlight the fact that Tom Willis, do you know who Tom Willis is? Paul Willis's son. So although it says Tom Willis 1 year in Aaron Connect, what it doesn't say is son of operations director for F&B, and has spent more years in microtunneling machines than you shake a stick at. He left them and come work for us. But that's the kind of years and number of experience. That's the team we put on it to keep it running, to keep it operating, to achieve what they wanted to achieve. Again, just like Bryn said, you're going to do an ultra long, you're going to do something of this nature, something has got to be going in your favour, and the ground has got to be in some way, shape or form ideal for the machine, the way the machine performs and the technique you're going to operate under. Effectively, very much like the Castle Rig, the ground was very stable, it was very weak rock. And this gave us the opportunity to understand that the annulus would stay open, and particularly bear in mind now, this was over nearly 2 kilometres long. There were no interjacks, there were no second chances with this. Whatever lubricant went in at the front was the only lubricant you were going to get in. So needless to say, it was pumped in at high speed and quite a lot of it. Some difficult geology, not totally difficult geology, but there were versions of boulders and conglomerates and clays and such like. And again, the separation system, the slurry pumping system, they were all designed with the possibility of repair, but with some sort of duality, some sort of replacement in the system, overlap, sufficient capacity that you could lose one and still cope with it. Somebody says, what is tunnelling? It's picking a daily fight with God. The last man to see what was put in the earth was that man there, and that's the tunnel engineer bowing down and saying, please can I have perfect tunnelling medium everywhere in the world? And God says, no way, you're a tunnel engineer, you deserve to be punished. Except in Army Bay in New Zealand, where I will let you have it. And that's long and the short of it. That was described to me. So, that's what he gave us. That's what Army Bay is. And that's why it was achieved. Low abrasivity, maximum strength 25, 30 megapascals, but most of it was in the 8 to 10. Low permeability, so there's not, just the same as you had at Castlereagh, there's not water coming at you constantly, high pressure, hitting the machine, hitting the annulus. The material was relatively easy to separate. There was not a large quantity of clay or a large amount of whatever clay we did have did not go into solution. Graham described earlier, you try London clay, you'll beat it to death. You do chalk, and if you do any length of drive in chalk, you can put 100% of it into solution. It turns into one thick white paste. It's horrible. It takes all sorts of frame and press separation equipment to get it apart, to get it to tip. Enough fine particles to create a plug, to create some strength. And the ground was generally extremely stable and supporting for the annulus. That's the machine coming out the end. That was it after being rescued at sea. And that's the kind of wear and tear that were on the teeth. Now, a couple of them, I think a couple of the bucket teeth, the external bucket teeth, were replaced as it went through the shaft, but by and large, you can see, these are called TCI disc cutters. Anybody knows about disc cutters? There are 3 main types. 2 look the same, and these are the ones that look slightly different. The 2 that look the same are just one sharp ring. And the sharp ring is either a monoblock, and you tend to use them in chalk, because chalk is got flints, and flints is ultra hard and will shatter anything, including tungsten carbide. So you have them made out of machine steel because they don't break, and they crack chalk, flints. There is tungsten ring roller cutters for hard rock, and then there are these TCIs for what's known as soft rock. And the reason is that in soft rock, disc cutters have a nasty habit of not rolling round and round and round. They break rock by constantly turning. The force of the machine on the face turns the rock disc cutters. But in soft ground, they have a habit of digging in. When they dig in, they go flat. When they go flat, you then have to go in and fix them. That was the jacking force, 360 tons. Now, I will say, around the outside of a direct pipe, don't know what your annulus was at Castlereagh, 25 mil, 30 mil? Right, okay, about, on the direct pipe, we have about 55 millimetres of annular space. So we have got more space for the pipe to flap around in. Any of you who've done HDD work before know full well that HDD guys need half as much as Gen. So if they drill you a 48-inch hole that you're looking at, they'll be able to pull a 30-inch pipe into it. And they will tell you with their hand on their heart, don't worry pal, the bentonite mixture will keep the ground open underneath your railway. Yeah, like I believe that. Sort of 12 inches around the outside of a pipe. Sometimes it does. Bentonite stays wet, it'll stay. Okay, so conclusions, and this is why it works. So this is where the caveat about be careful if you ever go specifying this, phone me up. Yes, it takes a lot of involvement, it can be done. It just happens to be it's a world record, it's extremely long, extremely careful. So the design, the alignment and the planning were all designed to work with the geology. They knew what the geology was, they planned the drive to suit the geology, to suit where they could put reception and intervention shafts. It says it's not a budget option. It isn't a budget option. That much kit does not come cheap. It becomes a hell of a lot cheaper than £50 million. People who want to know and understand what the risks are, and then people who do actually are prepared to take what's their fair share. Expert personnel. McConnell Dowell are a good microtunneling contractor, so I don't think they were inexperienced. They're very, very big in Australasia and all over the Far East. And they're also a massive civil engineering contractor as well. It was McConnell Dowell that did Waterview, which was a 15-metre EPB in Auckland. So these people are tunnelling people. They know their work. They have a lot of skill. I actually know the tunnelling director. Okay. This was put in by my German compadres. all the guys that went out there loved it. It was a great place to go and live and work. And the ground conditions were as if you had designed it yourself. So long, complicated can be done. It has to be planned right, and it has to have the right involvement and the right risk sharing. The end.
Thank you, Richard. We'll take some questions at the end. Our last speaker for the day is Ovidio Fronza from Barhale. He has a case study. According to this, it's the River Thomas crossing, but I assume it's the River Thames crossing.
Hi all. I'll present just about the pipeline tunnel project that we recently completed. So this was part of a London gas main replacement that's currently undergoing in London. 29 kilometers of pipe being replaced. So we've been challenged to bring a 500 millimeter gas, medium pressure gas from north of the river Chelsea to south at Battersea. And working back from doing the space proofing, we determined that we could need a 1.8 meter tunnel. And due to the size of the TBM selected, we constructed a 6 meter reception shaft at Battersea and a 7.5 meter shaft at Chelsea. There's a program that was stretched over 3 years, as I said, recently completed. So one of the main constraints was that at Chelsea, there's a Royal Chelsea Flower Show, so we had to break the works so that we can reinstate the shafts, construct the section of the work, and then come back and do it again. So we've done that 3 times. So we built the shafts and then tunnels, and then we installed the pipeline inside. Another constraint was that we were around one of the more famous project in Tideway, so we had to kind of work around them and try to demonstrate that the settlement caused by our tunnel is not going to affect Thames Tideway. So quite a lot of clearance, 7 meter to one of the connection tunnels, and 12 meter to the main tunnel, but not as in the previous cases. The ground conditions were not as we would like to have. So in Chelsea, as I said earlier, main constraint was that we had to have enough space to set up the site to drive the TBM, but also to backfill quite quickly because we have only windows of few months to do our sections of work. At Battersea, conditions were different, so there was quite a lot of large trees, up to 1 meter, so we had to ensure that our shaft doesn't affect the trees. They had tree preservation order. Also, the shaft was very close to the river, to the Thames river wall, about 4 meters away, and top of that, the topography there, so we had about 1,000 meter available. However, when we take out the embankment and the footpaths that we had to leave open, we only had like 40% of working area available to us. So we had to consider how we're going to remove the mark, how we store it, materials, plant movement. So in a way, it's probably better when you have less space because you'll spend more time in planning and how you're going to put it all. So the shaft is going to be located in the center around here. Like I said, quite close to the river. Also, we had to do a large program of monitoring the settlement. So one of the features we had to establish how we're going to put all the structures, all the temporary works, really in such a confined space. So with the retaining wall, we include that in a collar as well, and in the platform for the cranes, so that everything was pretty much on top of each other. But just to accommodate the large plant required to excavate the shafts, which are around 35 meter deep. Conditions, 5 meter bed ground, is quite good. Then we had a 5 meter of alluvium and river terrace deposits, which is a permeable ground. And this is what the problem we had, being so close to the river and other structures. And then 35 meter of London clay, which is quite good. So we need to come up with a solution to enable us to build a structure to the wet ground. to the wet ground, and then continue with the most feasible method. So we selected casing method to go through to the permeable strata, and underpin method once we had good ground to dig. Short animation showed how we did it. So we've done a cutting edge at the ground level, followed by a choker ring. Then we built a collar around it, 50mm space between those two to enable lubrications to be inserted. And with jacking gallows, and we built the shaft submerged. A bit faster than that. So when we reached clay layer, we replaced the cutting edge with a transition ring, and then we carried out the structure with an underpin, and we constructed the under-rim base. Test of quality control, a key function to ensure the shaft is done properly, and tunnels as well, is how you're grouting the annulus. So traditionally we have pressure sensors in the ground lines, but they're not always indicating the right, if you really have grout behind the shaft. So we developed we used like something quite easy to purchase off the shelf, a thermostatic camera, which showed us where there is grout or not. That enabled us to go and address those locations that didn't show any heat resulting from curing of the grout. Some facts we discovered: so in blue line the shaft, the reception shaft of Battersea; in orange the one at Chelsea, the drive shaft. So casing method, quite a lot of time spent to remove the cutting edge, and underpin method to follow. TBM selection, so we had a good corridor of 35 meters of clay to construct the tunnel, which was quite ideal for open face TBM, cheap and fast. However, there was in the vicinity there was presence of drift hollows, which could mean that the grout could be a little unreliable there. So we selected an Isaac ankle mole, 1.8 meter, able to crush boulders up to 500 millimeters. Point is earlier about steering joint, how you align the TBM with your theoretical line, and then a point we setting out. We use a pipe laser in the shaft, so we control the 330 meters from one single point with a standard laser. Bit about launch shaft layout. So jacking rig, we use a 600-ton jacking rig, and then we use the spacers to enable to achieve more stroke, so that we can push the pipeline sufficiently to enable placing of a new pipe. Quite small shaft, so we had to plan everything properly to ensure that we have enough space to land the man rider, so there isn't sufficient space to put ladders in. On a 35-meter shaft, ladders are probably not very effective because you spend quite a lot of energy going up and down on them. Quick animation showing location and what happened in real life, pit bottoms and up. So the total thrust load that we predicted was 1,200 tons. So the capacity that we could put on the thrust wall on the back was 600 tons. Also the capacity of the pipe as well, limited to 600 tons. So we decided to introduce two interjacks to distribute those loads. So we discussed a large about interjacks. I'm not going to go into too much. What we discovered though, in dotted line, this is the theoretical thrust that we would have experienced for that tunnel. The blue line represents the main thrust on the back wall. We introduced an interjack at pipe number 20 and at pipe number 40. Key was that the lubrication was quite effective. So in essence, even though we introduced this interjack here, we didn't utilize it until pipe 97. So that's quite key because the jacking forces will increase with time. So the more you spend in clay, the clay will distend and it will put more force onto your pipe. So essence is that even if you have the interjack as a backup plan, you're trying to thrust everything from the back wall. So to enable going one step back to get the most effective lubrication and the most effective separation, we took samples additional to the borehole records. We took more samples when we excavated the shaft. This enabled us to fine-tune the separation plant, also to fine-tune the lubricants and the polymers that we're going to use to separate the soil. So we're segregating the water from the ground. Schematic, there was something presented before, so just in summary, all the mud coming from the TBM screen 20 millimeter and this clay ball, then is descending to going to descending unit, particles above 6 millimeter and 0.03 millimeters removed out. Then a tank called dirty water. There's a process called flocculation where particles are attracted by adding a polymer and then spin into a centrifuge at 4,500 revs per minute, and then the result is clean water. You can nearly drink it, but it's quite good, and that's key for a success of a slurry project. So, as discussed earlier, this is the nerve-wracking moments for all the surveyors and setting out engineer how we're gonna ensure that this TBM goes into the right place, and then we have many arguments that the tolerance in the portal is too small, but we managed to take it in the right place, which is a good thing for us. Some interesting facts to take away, we discovered in terms of settlement monitoring and predicted settlements. We surveyed both Chelsea and Battersea shaft, and we established that the casing method was much better in terms of settlement than the underpin method. That was on both shafts. Both were under the predicted value, but the casing method was really good because effectively we had continuous phase pressure support provided by the cutting edge and the lubricant that was inserted. Some key facts. Project is expensive as a good car here. Duration, name of the project, tunnel as long as the shaft, and there was zero lost time incidents. Not a short video, hopefully.
Well done. Just nothing to do with tunneling, yeah. Just well done for keeping the computer working.
Okay.
Thank
Questions?
you. What a great way to finish the day. We thank you to all the speakers in this last session. There's 3 very different case studies. Shows the range of different things that can be done with these technologies. We have some time for questions to any of the speakers today on any of the topics. So now's the chance. The chance to get on. Yes, sir.
How do you overcome the challenges of voids? That could be man-made voids in the ground, where the seas, financials, etc. All around cars. With great difficulty.
Do you want to?
I guess the real answer is understand the site, understand the ground. If those risks are apparent to you, try and avoid them or deal with them before you get to them. So in the case of mining voids, you'd need a comprehensive SI which would identify open voids. You would then pre-treat them before you actually mine
To
anywhere
give you a
near them.
recent example, in Scotland,
Shieldwall
Tunnel, they knew there were a lot of mining workings with a very comprehensive grouting plan. In
However,
terms of,
I was going to say, if all of that fails and you do come across a feature, then I guess you have to do what you have to do at the time. And they're all different. So solution features will be will act in a completely different way to a man-made void.
you tend to find you find them by default. So the face pressure goes completely, no matter what you put down, it brings any back. Or you get no luck back. The technology, and it's not in the micro tunnelings, so don't ask me for it in the smaller stuff, but in the bigger tunneling machines in Kuala Lumpur in Malaysia, they have a lot of cast features, big holes. And there is a particular type of machine called the variable density where we have the capability of sending rock, or particularly a high density slurry mix with sand, bentonite in suspension, back into the hole to fill it up. The short answer, it's not an easy thing to deal with. They're very, very complicated things.
It is possible to do that with a slurry machine as well.
Yeah.
So an example which is not strictly what you asked about is we pulled machines back from already excavated faces. So if we come across a reinforced concrete pile that the tunneling machine can't deal with, we've actually pulled slurry machines out of the hole and filled the hole with the slurry system as the machine is retracted. And I guess that would be possible. The problem is with the pipe jack, if you're going at slow speed and you hit one of these features, the machine is likely to drop off the end of the pipe before you actually are able to do it.
That word mentioned a few times today, chalk.
Yes.
Yes, solution features.
Solution features.
Yeah.
It's rare for them to be empty. Now, if you're from anywhere around Watford or such like,
No, no, that's
right, near Watford there's a fancy hotel called the Grove.
yeah.
For a long story short, I sank a shaft there. About 6 months after I sunk it, they built a health centre on top of it. They said, oh, your shaft's all leaking, it's all bent and cracked. Turned out it's a solution feature underneath it that nobody knew about, and the whole shaft twisted in an 8.32 cubic metres of gravity into that hole. They are very, very difficult, they're extremely difficult to find. Some technology is out there that gives you half a chance, but you have to have a machine big enough to be able to drill profiles. They are a problem, even now. Nobody has all of the answers to that question.
But I think avoiding them is the
So, the only ground you could come up with that we can't cope with, you came up with.
That's the whole point, isn't it, to answer all the questions?
Where?
Just to add to that, having the facility in the TBM and the TBM driver and the engineer that's checking the facility to observe that there's a drop of phase pressure. So that will be able to stop before you get into it. Kind of speed. So close control of the operation will enable you to stop before it gets bad, and then you can stabilize that somehow.
Certainly the one I've seen, the
chalks tends to be overlain by versions of gravel. So all around Watford, etc., you'll find gravel bits overlaying the chalk. So you do see the cast features. You're going through chalk, and then you go through 10 metres of gravel, and then you go back into the chalk again.
Because I know that they're present below sort of basically, you know, the Millennium Dome, and they're present below that. But,
The Millennium Dome, they're a hell of a long way down.
yeah.
Depending on whether you're talking about pingos or there are some. There are some, but largely they're filled. When you're that far down, they tend to be filled with gravels or other type material.
Okay, thank you. Any more questions? No, everybody's anxious to get on the road. All that remains for me is to, on behalf of UKSTT and the Pipe Tracking Association, to thank all of today's speakers, to thank all of you for coming. I hope you found it worthwhile and informative, and to wish you all safe journeys home. Thank you, everybody. Thank you, speakers.